Okay, so hello everyone. As always, thanks again for coming on Friday to be with us and to learn a bit more. Today we are going to continue with SER, and I think we are almost finishing with SER. Probably next week will be the last class, or maybe one week more, but basically we are almost reaching the end. So I think this is very exciting. And then we will move to RH. So I'm really happy that you have been with us all this time, and I hope you will continue for a few months more. So then let's start with today's class. We would learn how to run SER in parallel, but this time for performing inversions. We will embed the iron 630 pair, so 6301 and 6302. And then we will also embed together with iron 1.5 micro. This is for showing you how to embed together two different lines that they don't go as a blend. So you have two entrances in the wavelet file. The idea is that this is a continuation of all the things we have done. So last week we did the synthesis. So then we are going to embed those profiles. Remember that we ran the ideal script where we put everything in a proper format and we added noise just to make it a bit more realistic. And everything is included in folder day 9. And the idea is that we will run the inversions with a given configuration. And then I will show you how I usually compare with the initial atmosphere, just to check if the inversions are working okay. And then from that, you can also tell things about the spectral lines. So then the atmosphere is the previous class and is the one that we transform and put in the proper format in day 8. Okay, so this is just a continuation of all the things that we have done in the 2 previous weeks. And I will try to focus and go slow on things that are not extremely related with SER itself, but it's something that we have been adding when we were working on the parallel wrap to improve the inversions, to improve the way we interact with the code. And these are all also translated to desire. So then it's something that you can use on the future as well. So as always, I just want to check if you have found a really strong limitation or something when trying to run the code. And if not, I will continue. But if there's something that you really said, okay, I found this and I don't know how to solve it, just let me know now. Or if not, as always, just try to write it down on Discord or contact Ricardo or me. Okay, so then let's go to the folder where we are going to run things. So as always, we will have in day 5, we will have figures, but we will go later to them. I will show you what they are. And then we have in this class, we are going to use the parallel wrap that is in this folder, but we are going to read the synthetic profiles that we created in this folder that I shared with you last week. And then when we are comparing the results, we are going to read the initial atmosphere that we computed in this folder. So we are keeping these 3 folders today. And the idea is that we are going to go back to them for the inversion, so in this case, and for checking the result of the inversion in this case. Okay, so then let's start with initialization.input. Okay, that is here. It's very similar. So the format is the same, and basically we don't need to change too many things. So let's go step by step. We define the number, of course, and this always depends on your computer. And then we are going to embed profiles. So then remember that we created two files, two fits files, one for each line on the grid file. So I mean, if we have a blend that is for the iron lines, we create one file with the 2 lines together, and then a second file that will contain the 1.5 micro. So the idea is that our wave grid file for the inversion should be the same as for the synthesis, and is this one. So then as we have two entrances here, then we need also two files separated by comma in this part, okay? So these are the two that we created adding noise. Then, as always, we need to define coordinates. I picked this for an example later, so I will show you why. And then debug, remember, one is for saving specific folders or pixels that you want to repeat or check in detail, but 0 should be the default, because then you can run and it will not save extra files. Then in this case, I always use 1, but if you want to have more information about the cycles, because sometimes you run several cycles and then you want to see how the profiles are changing, you can do it. But in general, if you want to just run over a given field of view, just put 1 here, okay? Then in this case, we are going to use this sentence. There are several options. I will not enter in detail today. We can discuss, if you really want to work on that, we can discuss it in a different class or just by mail. The idea is that the code will allow to pre-compute a given atmosphere, sometimes with neural network procedures, and then you can use that for as an initial atmosphere for the inversion. But this is a very specific case, and what I want to cover today is the standard case that you should always follow, and then you can complement with additional cases. So, but this is the standard one that I recommend you to use. And here, what I'm saying is that I want the code to check over 12 atmospheres. I will enter on this later. The idea is that the first number is the number of atmospheres that the code will use for run the inversion. And then we added an extra option that is after a dot. That is the chi-square value that you want to set as a threshold to tell the code, for example, even if you don't put anything here, so if you put this, the code will run the inversion 12 times with 12 different atmospheres and will pick the best value. So then this means that your inversion will be 12 times slower than if you put here 1. But we wanted to try to speed a bit things, and we said, okay, you can put 12, but you can put a reference chi-square value where you said, okay, I think this level is good. So then we're telling the code, if you run once the inversion and you already get that threshold, then don't go, you don't need to run 12 times. So then the idea is that for some pixels where they are very complex or your configuration does not reach that value, you may run 12 times the inversion. So that pixel will take 12 times longer than a normal pixel. But in other pixels where maybe the configuration is more suitable or the pixel is less complex, then maybe with 1 or 2 runs, you will reach a good fit, and then that pixel will only take 1 or twice the time of inverting a pixel. So then we are reducing the total time with this option. I will show you exactly how it works, but it's just to know what is the first number and what means the second number after the dot. Again, we did the synthesis looking at this center, so then we are going to do the inversion in the same way, but in principle, if you have an observation and you know the heliocentric angle, then you can put numbers here, and then in principle, the code will work trying to project the line of sight respect to your heliocentric angle. This is not used in inversions because you are going to provide the atmospheres, and those atmospheres, they already contain the macroturbulence, the filling factor, and the straight light. So this will not be used. And then, as always, you tell the code where you tell the wrap where the ser.x is located. Okay, so before going to run the code, as we are going to do inversions, so let's check that we have to define some files. The wave grid is the one I show you here. And I just copy the one from the synthesis and put it here because it's exactly the same. And then we have also the control file. So in this case, as it is, as it is an inversion, we need to put a value larger than 0 here. I created a reference configuration for the class, but you can always change it. But I tried to make something standard that in principle you could use almost in any observation. And I put 3 cycles, and then profiles will be generated by the wrap. So then you don't need to take care about this. We are providing it through the fits file. The grid is the one that we saw. Lines, LTE, and Asplund, the abundance, these are included here in input files, and they are the same files that we use for the synthesis. And then this initial atmosphere will be created by the code, and they will come from this folder. So here you see that there are 12 atmospheres. So then the code will take atmosphere number 1, will save it as initial.mod, and then we will run. So then you should not pay attention to this one or to the other one. This will be generated internally by the code. And later I will explain how I created this one, okay? So for now, just assume that the atmospheres here are the ones that the code will look for running your inversion. And from here, it will change the atmosphere several times, in this case, 3 cycles. And then you will get a final atmosphere that comes from this initial guess after perturbing in the given node's location and interpolating between the nodes. I just put some weights reference. So usually this is a white sand map. So then Stokes Q and U signals are not going to be too large. So then I just gave more weight to Stokes B because there are some network patches, and also Stokes I. But this always depends on your observation. And then very, very, very simple strategy for temperature 2, 3, and 5 nodes, and then magnetic field 1 to 3, and line of sight velocity 1 to 3, inclination 1 to 3, and then azimuth I just put 1, 2, but we don't have a strong Q and U signal, so you can even put 1. And then I'm not inverting microturbulence and also microturbulence, because when we did the synthesis, they were 0. So I think it's better to just, for consistency, to also keep them as 0. Okay. And then with the rest is usually the default. So then we have defined our inversion configuration. We have also our grid file. So then we are ready to run the code. Okay. So then we go to the folder where we are. We have the Python wrap, and then we just type Python 3 parallel master. Okay, and then we are going to run 4 times 4 pixels. Okay, and then it's going very fast. And I will explain you what is on the screen, and then we will do a second run. So the idea is that the code will always print the location of the pixel, so X and Y. It will tell you how many atmospheres it used for running, and it's saying that it ran 1 atmosphere. This is the time that it took for running. This is the pixel location respect to the full map that you ask for inverting. So in this case, it's only 16 pixels, so this one was located in that position. It's giving you the chi-square value. This one is the chi-square that we compute externally from Z, and it's the chi-square that comes from the difference between Stokes I only. So this is for the wrap, for defining the clustering threshold. So we wanted to keep it as simple as possible, and it's just different in Stokes I. And this is what we are going to use for defining the clustering threshold. So you can see that we have .5, so it means that we are asking the code to obtain an inversion that produces a chi-square for Stokes I lower than 0.5. Okay, this is what .5 means. So then you can see that in all the pixels, it only needed to run 1 atmosphere, and in all the cases got lower than 0.5, except in the last one that it says that it ran over 2 atmospheres, and then it picked the second one, and also the result is below 0.5. Okay, so in this case, the inversion was very fast, but the idea is that it's because it's not doing its best. So what I mean is that we have put a threshold, and I'm going to already change it while I'm talking. So I'm going to lower down, and I'm going to run. So then the idea is that we put a threshold that I would say that is relatively low. So then the code just ran it once, and it was fast. But I think we can improve the fits without really making it very slow, without it really needed to run 12 times all the pixels. So then this is what I'm doing here. So now it's taking more time. Before it was an average of 6 seconds per pixel, and now it's going to 15 or 27. But you can see that in some pixels, so let's go, this is 181.0, and then this is 181.0. Well, this one is the same, and some pixels we will see that are a bit better. And then I will explain you what the code is telling us in different cases. So for example, in this case, it ran 2 atmospheres and it took the second one. And in this case, it ran 4 and also took the fourth one. And then this is 5, and then this is 5. And then this is only a strange case. I think there are 2 strange cases in these 10 pixels. And the idea is that it's saying that it runs 7 times, but it picked the 5th atmosphere. So just let me try to. And this is because we think this is the best way, but it sometimes could lead to some confusing behavior. So the idea is that every time that we look for the best chi-square when we have run, so I mean, the threshold for defining how many times we run the inversion is given by the parallel wrap, and is based on the difference of Stokes I. So it's a chi-square that we compute externally. But when we reach that point, the code looks for the chi-square from SER. So then, because this is the one that really contains Stokes I, Q, U, and V, and is the most accurate one. So then what the code is saying is that in this case, for example, in this one, the code reached the threshold in the 5th inversion. And from the 5 inversions that we ran, SER had best chi-square in the pixel 5 as well. But in this case, what happened is that we reached the threshold for Stokes I in the inversion 7, but the best global chi-square is in pixel 5. This happens, I think, twice. I think only twice, because in this case, what is happening is that the chi-square is not below 0.1. So then in this case, it ran for the 12 atmospheres, and then the best chi-square from SER, it happens in different cases. Okay, but in this case, we never reach the threshold that we imposed. So then let me try to go back to this case where we reached the threshold, but the best SER chi-square was in a different atmosphere. So the idea is that we wanted to create an option for telling the code that we want to have some threshold, and we wanted that that option didn't depend on the configuration that you have. So the idea is that the difference between Stokes I, and if you put a threshold of 0.1, it will not change if you change the configuration of the control file. If you put more nodes on temperature, if you put more weights on Stokes I, this threshold will be the same. But the chi-square that SER is defining, it changes based on your configuration. So it was not easy for us to define a general value that you can say, okay, I'm going to change my configuration, and then I still can trust this threshold as the threshold I want. So then for this reason, there's this discrepancy, but the idea is that between one configuration, if you run it different atmospheres, the best value or the lowest value is usually the best, so that is kept. And what we are allowing you is that if you change now the configuration of this control file and you change, for example, here and you put, I don't know, 7 nodes, you can still trust that the threshold that you use for the previous inversion is going to keep the same meaning. So then you can run different configurations and you're still trying to reach the same goal. So for this reason, sometimes you can get this discrepancy, but as you can see, it's only twice in 16 pixels. So what we are doing here is getting, in general, better results. We are making it slower because in this case, it ran 12 times for more than half of the pixels. But this is because this is a complex region where I knew that the code will struggle a bit with this configuration. But you can see that sometimes the solution doesn't, so it is changing a lot depending on the initial atmosphere that you use. So I think you can always play with the threshold to make it a bit faster, but trying to always be on the safe side, so trying to make it a bit demanding. So what I'm meaning is that now it took 1 minute and 39 seconds because several pixels took, they needed to use 12 atmospheres. But this is a magnetic patch. So if you go to the corner of the map that is just quite sun and you run it again, you will see, I think, that most of the cases in this example, they reach the demanding threshold with 1 atmosphere. So then what I recommend you to do is when you have your map, pick several cases. For example, imagine that you have quite sun and then you have complex scenarios with a network patch or the thing. So try to pick several places and try to define a threshold where if the region is relatively normal, like quite sun, you don't need to run the 12 atmospheres or the 10 atmospheres that you have. So then the code will be very fast outside complex areas. But at the same time, when you have a complex area, ask the code to really push for fitting the signals there, because otherwise you may be not really fitting Stokes B or Stokes Q or U. So then try to find a threshold that is a balanced one, that it's not always running with 1 atmosphere, but also it's not always requiring to run 12 atmospheres in all the peaks. Okay, I will show you how the map of the atmospheres the code use look like, but this is a good example. So in the quiet sun, where Q, U, and B are basically noise, the code just runs with 1 atmosphere and the fits are very good. And in the case where we had complex pixels, then the code struggled a bit more, but it tried to fit as best as possible with our configuration. Okay. So then, okay, so now we have run the program. So we know how to run it and we know what is happening on the screen. We have almost all the ingredients. I would like to explain you the last ingredient for running the code, and then we will check the results. So the last ingredient are the atmosphere itself. So I prepare a file, a folder here that is called atmos prepare. And I put it in this folder, input, several reference atmospheres. They are basically all the file models that we have and HSRA. I put here some explanation. The HSRA is this from this reference, it's a quite some model. And then the file models were extracted. I think Basilio was the one that computed them. I think, yes, right? Yes. And then this is a very quick explanation of what they represent, but there are additional ones. But I think with this, you can already create a map of different atmospheres for the initialization of the inversion. So then what I do is the following. I'm going to read the atmosphere from this folder, and I will try to follow 5 rules. The first one is that the models, they represent different physical scenarios, so that the temperature stratification is usually different. So one is cooler, one is hotter, and one has some variation. So I recommend you to read the atmospheres and create one or two perturbations of that atmosphere, but I would not change too much the temperature. It's better to have different models that represent a different nature on the sun than modifying one model the temperature a lot, basically because I'm not changing the electron pressure. So I just change a bit the temperature or not at all. Then you need to, when you create, so the idea is that we will read an atmosphere, we will perturb it, and then we will write like we did in the previous class. So the idea is that when you write the atmosphere, the name should be so it means the atmosphere for clustering. So it's a ATM-CL, and then plus a number. So 1, 2, 3, 4, 5, and until you want to keep the code. So if you want to have 20, it's fine. 30 is also fine. This is really important. So you are going to create atmospheres, and they come from different models. So you may have an atmosphere from a sunspot model or a Umbra model that you had from the past, or someone passed you. So it is that you can always integrate them, but it's important that you keep three things in mind. This is critical. So you cannot provide an atmosphere cluster 1 with 50 points, an atmosphere cluster 2 with 55, because it's not possible to create an array that has these fluctuations. And also the nodes will also be different. So you have to keep the same number of points. And then I think for consistency, you also have to keep atmospheres going to the same lower boundary to the upper boundary. So if one atmosphere goes from log tau 1 to log tau -5, then the rest of the atmosphere should do the same. And then this implies also that the optical depth step will be the same. So if they have the same number of points and they cover the same optical depth range, then the step will be also the same. But try to keep these three things equal, because you don't want to add additional effects than just the configuration, the initial configuration of the atmosphere. And then this is a recommendation, but still a strong one. Just try to keep things as varied as possible. So a positive velocity, a negative velocity, a strong field strength, a low strength, an inclination of lower than 90 degrees or larger than 90 degrees, but always constant with height. Because as I show you in the beginning, if you start with one node, the code will just move up and down the atmosphere. But if you have a complex stratification, it can already induce some artifacts. So just make it simple, everything constant, and then let the code work. But any variation is fine. If you want to start with 100 Gauss or 2000 Gauss, it's fine, but just try to keep it constant. And then this is an advice, and I think it's like future-proof. So remember that when I said here, I said we are going to put microturbulence 0 and microturbulence 0, so we are not going to embed it. But you may want to try it. So then if you prepare the atmospheres with a non-zero value in microturbulence or microturbulence, then running the inversion will have no effect, because this is centimeters per second. So you can imagine what is the impact of this on the Stokes profiles. And the same, this one, well, this one is in kilometers, but it still is very small. So it has no impact. But as SER makes the perturbation as multiplying, right, Basilio? Multiplying the initial value.
Yes, it's a proportional change.
Yes.
Relative change. Okay.
Yes. So then if you put 0, then the code said, I cannot change. I cannot make a proportional change of 0 because it's already 0. So then just put a very small value, both in microturbulence and microturbulence. And if you don't invert it, it will not have any impact. And if you try to invert it because you are just doing test, the code will not complain. Okay. So this is just the final step of the recipe. So then just let's check an example. So if we go to Yes, go back and then go to Atmos prepare, ITM, and then, okay. So I'm reading the HSRA model. And the first thing I do is that I want to have a given optical depth range. And I check it, and I thought that from log tau 1 to -5 should be enough. So then I'm going to pick, the initial model has more points. So then I'm just taking the points that go from that range. And then this is, just 1 second. So if I just let me put a stop here. So, so then if I do, so the step is 0.1. So just let's tau from 1 minus tau from 0. So then the step is 0.1 or minus 0.1, depending how you start. So then, and we have in this range, so 61 points. So you can see that with this configuration, we are covering a given range, and the number of nodes that we have is also very flexible. So we can do the inversion with 1, 2, 3, 4, 5, 6, 7. So this is a lot of freedom. So then if you create for photospheric lines a set of initial atmospheres with this strategy, so from log tau 1 to -5, with 61 points with a step of 0.1, then you are already getting a lot of flexibility for choosing the nodes, and also for allowing, in case of a complex atmosphere that can shift the formation of the spectral lines, you still have some margin until log tau -5. Okay. So then what I do is just play a bit. So for example, in this case, I'm adding a magnetic field of 200 Gauss. I'm adding a velocity of 1 kilometer. This is a downflow. Yes. And then this is an inclination of 45 degrees, and then an azimuth of 30 degrees. And then I just repeat this several times. So then I run another HSRA atmosphere, but now I put, sorry, this was an upflow, and this is a, no, sorry, this is an upflow, and the previous one was a downflow. So now I'm putting a different inclination that goes about 90, and then a different azimuth. So I just play with these values. If everything is constant with height, but then I add sometimes a bit stronger magnetic field or a weaker one, and then I use different atmospheres. So the first one are HSRA, but because I just picked them, but you can pick others. And then I picked FLF, and then the file P, and then file S, and the idea is that I try to make it consistent. So if you go, it says that file P is a Facula model. So then I try to put strong, relatively strong magnetic field and vertical, but you can change this a bit. And in the case of the sunspot model, the file S, this one, I put it a strong magnetic field, and then I put it also almost vertical and low velocities. So I try to make it a bit consistent with what we expect from the physical scenario that they are trying to reproduce. But the idea is that you can change those things freely. So it's not a big problem. The only thing is that be careful with the temperature. Don't try to make it too different, because it's better to just take a model where the temperature, electron pressure are consistent and are very different. Okay, so then with this, you can prepare any number of atmospheres. I picked 12, but you can pick more, or you can just copy the 12 I have and then just put here a lower value, so like 6 or something like that. Okay. So any question so far? Are you following more or less how to prepare and why we added external things to try to make the code faster, but at the same time to try to force to reach a good fit?
I have a question.
Yes.
Like when you put clustering equal to 12 and after that some value for chi, so 12 means it will check for all the 12 atmospheres which you are putting, but you showed that sometimes it can converge even with the 5 checks. So
Yes.
how it selects, for example, that number, like whether it's the first 5 or from 12, which 5 atmospheres it just checked first.
So for example, in this case, none of the atmospheres reach the 0.1 threshold. So then it ran all the atmospheres, and then it just check from all the inversions which one produced a best fit for SER. So it's checking the chi-square from SER, and it checks the one that produced a best fit. And in this case, it was number 2. And in this case, for example, was number 8. Okay. But for example, in this case, it only ran 5 times, and the best atmosphere was the last one, the 5th one.
So how it knows which 5 times it has to run? Which
Carlos, can I?
Yes, it has to run.
So, Carlos, can I?
Yes, because maybe I didn't.
So basically, the code will go incrementally. So imagine that you have the 12 atmospheres, and you need to give ATM CL1, 2, 3, and so on. So the code will always start with the number 1, and then goes incrementally. So if he runs the number 1 and he reach, if you don't specify the chi-square as Carlos mentioned, he just runs them all and picks the best. If you put the chi-square limit, it goes to the first one and check if the chi-square is already reached or not. If not, jumps to the second one, and then it checks again, and so on and so on. So he always goes incrementally.
Yes. Sorry,
and in the end, you get a fits file with the position of the index of the atmosphere that the code will at the end consider the best one for each position. So I don't know if it was clear.
Yes, it's clear. Like my only one confusion is like, let us say it has selected from the very first 5, it can reach some value of chi-square. But for example, it is not going up till 12th, and the 12th one could be the better one, better as compared to those 5.
Yes. I didn't understand the question. Yes, so the idea is that the number of atmospheres that you have here, so it will just go in a step in. So if you just put, for example, here 3, then the code will just read number 1, 2, and 3. It will not read the others one. And then if you put 12, it will be always an increment order. So it will try first atmosphere, then number 2, number 3. So it's always in that order. So if you have like 100, for reaching the number 99, it has to pass all the other ones. So it's always in incremental order. It will never jump from one to the other, at least when doing the inversion. Okay? Okay, good. I think there's another question.
Yes, Carlos. Yes. So is there any regularization included in the chi-square term? The user-controlled regularization or something no. Okay.
It's only the regularization that appears by the SVD, the inverting. When we are inverting the matrix, we put a threshold in the SVD decomposition, and this implies a kind of deregularization, because avoid solution that goes changing a lot through the depth. There was a possibility of to put a penalty in the regularization. There are some options, but are not explained here. You can select a regularization if you like. Some penalties over the change of the step, the slope of some parameter along depth. And then you can introduce some kind of regularization. In fact, we can implement some regularization if you like. For instance, if you prefer that the code runs with a previous regularization, we can include easily in the minimization.
Mm-hmm.
Okay.
Yeah, but so
Thank
far
you.
is so far is the normal traditional share chi-square. So we
Yes.
didn't add additional things.
The SBD. Yeah.
Yes.
Mhm.
Okay.
Hey, Carlos.
Yes.
Carlos.
Yeah.
When you look at the number of atmospheres it runs, right, in the example that you show, can you show that? It looks like the number of atmospheres it runs is always increasing.
Yes.
Is that just coincidental here?
Yes, it's because the time is increasing. So the fastest one are appearing first.
Okay.
And then the slowest one appearing later.
Yes.
So,
okay, so it's just the way it's listed. It's not the way.
Yes. It's just they appear as soon as one is finished, then it appears here on the screen. So then this one are the slowest. So then appear the latest.
No, I understand. Yeah, I mean, because that looked like suspicious.
yes, no. It's just because it takes longer. Yeah.
Yeah, understand.
Okay.
Understood.
Okay.
Yes.
Okay. So then no more questions. Okay. So then and then if you go to the README file, you will see that there's a lot of output files. We will try to go through them. So, but just keep in mind that if you don't know what is the meaning of some file, you have all the explanation here, and I will try to cover it today, but always keep in mind that you have it here in case you forget or you are not sure about what is something. So then, but now let's go to, so in this result, this is what we were doing now. This is all the files that we are doing now, but I run all the cube, the 500 times 500 pixels. So now let's go there because it's easy to visualize everything. And just as a reference, I put it here. I think it's this one. Yes. So running with the 12 clustering 12.1 sentence, it took for me 2 days and 6 hours with 30 CPU threads. And you can see that, for example, in the final case, as it is basically quite fine in the corner, then it's basically just one atmosphere that it needs to run to achieve a good value. But still, sometimes it needs to run several atmospheres. So this is what I wanted to really emphasize, that push for a strong threshold or a high demanding threshold, but one that in simple cases do not force the code to really run 12 times, just once. But at least that sometimes when the pixel is complex, it try to push a bit the code to obtain a better fit. Okay, so then let's go inside this folder. And I think we can go through the program, or yes, let's go. So I think I made a program here that is called script. And here I'm making some plots. So let's go through that. So then the first thing I did was to read this file that is the input profiles. So we are saving it at the same time. So then you can have exactly, because if you remember now, we are starting the inversion with these two files, but they are 500 times 500 pixels, and we are just running 16. So then what we are saving in this file are those 16 original profiles. So then you can really know what was the input and what is the output. So then these observed profiles in the previous example was 16, now it's 500 times 500. Then these are the embedded profiles, okay? And then, as I said last week, the wavelengths and the index, they are extensions of the fits file, so you can read it this way, okay? So then just let's check how the results look like. And what I did was a very, very simple plot. So I'm going to plot the original profiles at wavelength position 0, that is the continued at 630, the wavelength position 50, that is the rest wavelength of 631.5, the iron line, and then the position 401, that is the rest wavelength of the line core of 1.5 micron. I'm going to plot this in the first row of a multiplot, and then the inverted profiles are the same wavelength position. So then if we go to figures here, I already put it in Dropbox. So then we have something like this, okay? So in the top row are the input spectral features at given wavelength, and the bottom row is the fits. So you can see that in general, the configuration was working well, and the threshold that we imposed, it was working well because the results are really good. If we want to really check in detail, we can see that here is perfectly smooth, and then here we have some slight things, but this is because we have noise and the fits are not perfect. But in general, the results, oh, what is that? Sorry. But in general, the fits are really good. So you can see that they are very good. I didn't enter on a Stokes Q, U, and V because I leave that to you if you want to try it. But just for Stokes High, it looks that it's really good. And the important thing is that if you want to compare the Stokes profiles, these are the one that you use as an input, and these are the output. Okay. So now let's go to the second file that is generated, and it's this one. And this is the output atmosphere that the code found. I mean, the inferred from the inversion. And we are going to compare that to the atmosphere that we created with the parallel modelador that I put in this 500 times 500 folder. So let's compare it. And then the important thing is that I put here a print just to be sure that we are in the same scale. And you will see that if you read those two files and then you print this, well, I can do it. So if I do this, oh, sorry, I'm not in there. 1 second. And then results, and then 500, and then figures. So if I copy this, so then you will see that the index 10 in the initial atmosphere corresponds to log tau 0, and the index 10 in the inverted atmosphere is also 0. But this is because we decided this way. So it's the atmosphere that we use for the clustering has the same range, but it's not a condition. So it's just to be sure that now when we are comparing the same optical depth, we can use the same index. If you have a different height scale, then you should be aware of that. So when you're comparing the atmosphere. So then in this case, I'm going to compare at 10, that is log tau 0. Then at 20, as the step is 0.1, then this means that this is log tau minus 1. And then 10 points higher, this is log tau minus 2. And then I'm going to compare the original atmosphere with that that the code inverted. And in this case is the temperature. Okay. So then if we go to temperature, we have again that the results are really nice. So top row is the input atmosphere. That, remember, we use this atmosphere for synthesis, then we added noise, and then we inverted in starting with atmospheres that are really simple, FAL or HSRA models with constant stratification in the rest of parameters except temperature, and the code iterated until reaching a solution like this one. So in general, again, the results are good. As before, there are some cases where here this black is not as good as this one, and then we have some kind of pixels like this here that here look like a bit weaker or cooler. But in general, the results are really good because these are really small scale features. So it's working well. Okay, and then the idea is that I repeat the same for the rest of parameters. So for line of sight velocity, field strength, inclination, and azimuth, I will just go through them relatively quickly. Line of sight velocity, again, results are very nice. Log-tau 0, almost perfect. Log-tau -1, still really, really good. And log-tau -2, still good, but in some cases, the really low scale variations like this one here, okay here, but not exactly the same. But it's a complex atmosphere. And again, we are starting from a constant certification. So it's reasonable that some error is expected there. Then field strength, it's also looking good. Here we don't see this nice shadow that we have like with like threads of magnetic field. Here there's some gray, but it's not as well. But still, I would say that it's really good. So I think it's working, and the threshold that we put and the configuration we use was reasonable. Then inclination, it's not so clear because it seems that the original one, it's very complex. I don't know if this is because of the transformation of the optical depth or something like that, but it's relatively complex, although we are getting the general idea. But again, the magnetic field is not so strong outside the concentration. So then it may be that the signals, the Q and U signals, are close to noise. So we should not really worry too much about that. And azimuth is even worse. So just I put it here, but it's really complex, the one in the original atmosphere. But still, we are getting something. Although in this case, we may need to add some disambiguation because of the 180 degrees. So I just put it here, but it's very vertical field strength or weak. So then I should not, you should not worry too much about not getting perfect azimuth in this context. Okay, so then this is more or less how I just ran one inversion and said, okay, let's check if things are reasonable, comparing the atmospheric parameters. But now we have extra things that the parallel graph says. The first one is the chi-square value. So this is xy, so the field of view, times 2. And the first one is the one that we are seeing on the screen. So the chi-square that we're using for threshold. And the second one is the one that SER is computing. So then we can plot it, it's this one. And then in this case, it's not so easy to know if this is a good or bad fit, because I think we should compare with something. It is true that our threshold was 0.1. So then white, really pale values means that we are below that. And you can see that there are a lot of areas with those values. But it's true that dark, it's a bit far from 0.1. And you can see that there are some regions, but not so much. But I would say that this is okay. And the idea is that just looking at this is not so easy to know if it's a good or bad fit. So maybe you need to run with a different configuration and then compare with this one. The important thing is that this is what I said. So you can see that for SER, it goes from 0 to 2,500. But if you change the configuration, if you change the weights or the number of nodes, these values can change. It doesn't mean that the fit is better or worse. It means that the way it's computed and weighted is different. So it's not easy to compare these chi-squares computed with a given configuration with other. So then I just put it here, but again, without really comparing mainly these two, mainly this with a different configuration. It's not so easy to say that this was a good or a bad fit. But what I do is just check the atmosphere. So if they are okay, then you can start thinking that this configuration can be used for an observation of quiet sun or network patches, because the results were good. But at least you have the information. And the important thing is that the one here, the one from the right, is the one that defines which atmosphere we picked. So the one on the left is for telling the code stop running inversions, stop like in atmosphere 5 or atmosphere 7. But from the 7 runs or 8 runs, the value that the code will pick is the minimum from this array, okay? Because this one contains everything. It contains noise, factoring, and the 4 Stokes parameters. the nodes and the weights from the Stokes parameter. So it's the most realistic one that I still will present someday when, when I have time to read the program. I think when we are with Desire, I will explain you how exactly it's computed. So then you can reproduce it. For example, if you run 2 inversions, you can, if you want to compare them, I will tell you how to reproduce them. So then you can compare 2 inversions and check if one was really better than the other. Okay. And then other thing, this one. Okay. So then this, what is in this file is an X and Y file. And what it contains is per pixel, per X and Y pixel, it will tell you which atmosphere the code picked. Okay. So which index? So in this case, we have that index will go from 1 to 12. And if you make the plot, this is how it looks. So in this case, white is 1. Okay. So you can see that in general, just make it a bit smaller. White dominates. So it means that in regions where probably the configuration was not so difficult or not so complex, the code just runs once and goes fast. And then you see a tendency that it seems that in regions where the magnetic field is stronger, it's getting green. So it's probably between number 8 and 9, but I think this is the plush atmosphere, maybe. So then the important thing is that if you see these, it's okay in the sense that you are not really wasting your time because it's a demanding threshold, but it's basically staying with 1 in simple atmospheres. But you can even think of improving this, saying, okay, so if I see green most of the time, I can put the atmosphere green, for example, number 9, I can call it number 2. So then the code will run number 1, everything will be white. And for reaching the fit of green, it will be the second iteration. Because as we said, and from the question from Nancy, the idea is that it will go 1, 2, 3. So if you know that in general, the number 8, it's providing good results in most of the cases, then put it at number 2. And then 1 and 2 will appear much earlier. So I mean, number 2 will appear much earlier than 8, and you are also saving time. But this is something difficult to predict. So in general, you have to run once and then check how it looks with your data. And then from there, you can fine tune this a bit. But I guess, yeah, you can save time, but it's not the critical thing. It's just that it's clear here that number 9 was the dominant besides number 1, and number 12 sometimes appear. So then you can move number 9 and 12 down to number 2 and 3. And then probably with 3 atmospheres, you can cover the whole map. Yeah, there's a question. Alberto, yes.
Hi, hello.
Hello.
Can you hear me?
Yes.
Yeah, nice. Well, first I have to say that I don't really understand what you call clustering, but maybe it's a technical point. My question, it was more related that why don't you synthesize the 12 model atmospheres and look for the closest profile to these synthetic profiles and then use directly this model for those pixels that are close to a synthetic profile for model 3, for example?
I'm not sure why.
Yes, I understand your question. In fact, you can use other modes. That is, this is the origin of clustering, because you can use a clustering of the profiles as you are doing. Then there is a lot of echo. Okay, then you can initialize with the closest profile, with the closest atmosphere that is producing this profile in the classical sense of clustering as you are working with. Then you can start this inversion graph using a previous clustering of the profiles.
Yeah, that's what I understand, like clustering, yes. Exactly what you are mentioning now. But
because even, this is one option. Then you in fact, doing just like Carlos has explained, using 12 atmosphere and using one after the other, you can start with a previous clustering of the profiles and using the corresponding model atmosphere that is closest to this profile. And you can do that. And this is the origin of the clustering denomination of this.
Yes.
And then, in fact, you can do that. Carlos has not explained other possibilities of clustering, but this is possible to do.
Yes. No, but I think we are talking about different things. What you, Basilio, firstly explained is what I understand as well as clustering. You cluster the data, then you take the representative profiles, and then you make the first inversion, and you take this result, the model atmosphere resulting of this inversion of the representative profiles as initial guess for every pixel in the cluster.
Exactly.
That is what I would say a clustering-based inversion. Okay. What I'm just asking is, if you have these 12 models atmosphere that you have created from file C, file P, whatever, why don't you synthesize this atmosphere and you have your profile?
Okay.
And now you look for every single synthetic profile corresponding to these 12 atmosphere, you look the closest profiles in your data, and then invert this data, these profiles, the one closest to model 3, you invert with the model 3.
Yes.
Instead of doing the inversions and looking for what is the closest every time.
Yes, yes.
If I can,
but it's different. I mean,
yes,
I know it's different.
No, the question is. Okay, Ricardo. Okay, go ahead.
Okay, probably at this point, I agree that clustering can be a bit of misleading, but is also there for the lacking of better word or also simplicity of the initialization, not input. Because actually this field started with as Basilio mentioned, with a proper clustering. And we didn't want to, we can implement, and we have already ideas to implement other type of clustering or initialization, and probably it would be, maybe you are right, instead of putting there clustering, we can call it initialization. So the first part of this model was you just give to the code a fits file with the index for each pixel. And this index was given by you. So if you wanted to clustering, or if you wanted to split your map using intensity, or as you mentioned, synthesized lines and pick the atmosphere that create a profile that is similar to the observation, this you can do it. But we kept it at this part as the user side. So if you just put yes in clustering, as is mentioned there, the code is looking for this file, and then it picks the atmosphere corresponding to this file and just going to run this one. So it's not doing automatically, it's up to the user to decide the clustering method that you want to do. So you can also have the other two types of clustering, that is the neural network assisted, but yes, can be misleading that this clustering when you use several atmosphere, but this also was a later introduction to the code. So if everyone agrees that you should call it initialization and such things, we can change. And also, if you feel that it's better to have hard-coded clustering, like as you mentioned, you can add it later on, of course.
So
okay, but one moment.
Let me talk, Basilio.
Okay, okay.
So the idea is, but I think we are talking about different things, Alberto. So what I'm saying here is that I studied for a given atmosphere, I completely change it, and that one obtain a best result. So I'm not looking for starting with an atmosphere that has a synthetic profile that is close to the one that I want to embed. I want to check which atmosphere is the one that produces a best fit after changing a lot the nodes. So what I'm saying here is that the atmosphere 1 is probably so neutral, so flexible, that in most of the cases, when the code wants to change it heavily, it always produces a good fit. But this doesn't mean that synthesizing pixel 1 or 2, so I mean, if you synthesize the Stokes profile with that atmosphere, will be similar to the ones we want to embed. In fact, will be very different because we have a really, really complex simulation. But what we are seeing here is that when the code wants to change things, and want to really heavily change the atmosphere, introducing gradients and complex stratification, the first one that is a flexible one because it's a HSRA with constant field, is the one that is easiest for the code to reach a complex profile. So we are not saying that the synthetic profile from any of these atmosphere is close to the one we want to fit. What we are saying is that the code is changing it a lot. And in the case of the first atmosphere, is the one that for the code is easiest to change and to get a good fit. But I can tell you the atmosphere that we are training is really, really different than the one we are starting from. And for that reason, the profile will be also very different. So it's something different that what we are saying here.
I understand that.
Okay.
You can have
one thing. Not necessarily the first one is more flexible. The question is that just with one atmosphere, you have reached the threshold. And maybe it's not close enough. It can be far away, the profile synthesized. But you need to avoid, in some cases, local minimum. Then in some cases, you will need to start the program with several atmospheres because just with the first one has reached a local minimum and you don't have a good fit enough. Then
I understand that, and I think it's a group. I just asking if you have tried the other thing. Saying that, reaching a local minimum is a possibility in any single model. You can try 100, and you can luckily somebody life is hard. You get a local minimum in the 100. That is a possibility. It's smaller than if you try with one model. It's 100 probably, but you can have that. But I understand the approach that you. I just asking if you have tried or order, for example, instead of starting just for the first model in the list, order getting closer. But it's okay. Just it was just a technical question. I don't want to. Thank you guys.
Thank you very much.
Okay, so then, is there any question related to this? So does anyone or does everyone understand what we are trying to do in this case? Okay.
I just want to add that 12 atmospheres in general is not too much. In some cases, we are working with 25 or 30 atmospheres. Then it's okay. You can run the program. If you are looking for a very good fit. Stringent threshold value, then you can work with more atmospheres.
Yes. I think the key is to really think how different an atmosphere is from the others. I mean, you can cover like from -10, -5 kilometers per second and 0, and then 5 and 10. So then you have like 5 variation of velocity. And then you can combine that with, I don't know, 5 variation of magnetic field, 100 Gauss, 350, 800, 1500. And then you combine that with another variations of inclination, 10, 45, 90, 120. And from that, you can create a map of around 20 or 30 atmospheres. But I guess you probably should try, if you see too many difference between 10 or 30 or 50, and then choose the value that you feel more comfortable with. An important thing is to try to do this exercise. So you run it and you check for your physical scenario and for the atmospheres that you define, which ones are more common, and then try to move the most common one to lower values. So then this same run, if I move atmosphere number 8, 9, and 12 to lower values, then probably I can save like 20% or even more. So then the idea is that you can play with this a bit. But again, the code is really fast. So I think you should always try to optimize, but until some point. So if 2 days it's too slow, then try to optimize a bit. But if you are doing other things while it's running, so then 2 days or 1 day and a half should be the same. So just to keep in mind that there are some options, but I will not really spend too much time on doing this. So just to try to keep, as Basilio said, a wide range of atmospheres to avoid local minima. The atmosphere should be as different as possible to cover a large map of options, but just pick the value that you feel comfortable with, and if it's above 5 or 10, then you should probably be more or less okay. Yeah.
I'd like to add, if you want to use this program as a synoptic way, a systematic way, doing a lot of inversion, maybe the idea of using clustering in the sense of Alberto in the k-mean, using k-mean techniques or something like, can be very helpful because you will save a lot of time if you start with a closest atmosphere from the. Then these techniques can be very helpful if you want to use to invert many for instance, if you want to invert a temporal series, a time series of spectra of images, something like that.
Okay.
I have a question about that.
Okay.
Probably, I don't know, maybe it's for Ricardo. When you actually made the clustering that we are mentioning right now, can you explain us how do you make the cluster? Do you normalize? Do you scale the data? What kind of data do you consider?
Okay. The two modes that are already there that you really do some real clustering is the one when you use the neural networks, and for that you need to have already the pre-computed model. We have already for 2 lines, but our goal is to increase this database with more lines, and as soon as we have more inversions available. And the other one, is more simpler than that. The code just accepts indexes for each pixel. So imagine that it basically is you who is doing the clustering. You are just feeding the code with the clustering that you use, meaning that instead of having, for example, this 12 atmosphere, you have also 12 atmosphere, but tell the code that, okay, for the pixel number 1 is the atmosphere number 1, the pixel number 100 is the atmosphere number 6. So in that sense, you just need to feed the code with the atmospheres and give the positions where this atmosphere is going to be run. Then you just have 1 atmosphere per pixel. And then it's up to you the type of clustering that you do. We are planning to use some other methods, but yeah, we still didn't implement them using or some field approximation or something like this. Or as you suggested, that is actually a very good idea to use the synthetic profile and to estimate the best possible atmosphere, and that we can save time. But on the clustering mode, no, you just need to feed the code with the index of the atmosphere.
No, yeah, I understand that. My question, it was very more straight.
Sorry.
It was more like, what if when you are making the clustering of the observed profiles, when you apply, I guess, k-mean, or I guess you are using k-mean, but maybe you are using dbscan or one of these other methods. What input do you introduce? You normalize IQ-UMB, you scale IQ-UMB, you just consider I.
So the clustering techniques that I usually do is not hard-coded still on the code. I always normalize them. But,
okay.
It's still not implemented, as I mentioned, but I always normalize it. And for example, as simple as for when I run a sunspot inversion with a sunspot, I just simply cut with intensities, and it works most of the time. So then I have just 3 classes: quiet sun, penumbra, and
but okay, we can talk about that then.
Yeah, but if you use k-means, it's more complex, but then it's way more complex.
Okay. No, sorry. Okay, thank you.
Okay, so I think I understand Alberto's question, but I think it's not implemented, and I don't know if we're going to implement it soon. So I think it's better if you talk, but you can do it through Discord. So then people can follow the thread, and if someone wants to even add things, then please do it. So then other people can join. But today what I wanted to explain is the simplest way, and for me, I think the most stable, because you just know the atmospheres that you're running. You can run it every time, and then you can run different configurations, and you always have the same atmosphere. And that atmosphere that you use usually, so then it's relatively easy to transform them. And there's no limitation of making variations, so you can create a procedure and run perturbation of velocity, magnetic field, and other things like 100, and then you create your initial package of atmospheres that you will always use. You put it on the Atmos file, and then you have it for any map that you want to run, and then you can play a bit with the index files depending on which atmospheres are more common. So this is essentially the simplest option, and the one, for example, we used for the paper was this one. So we had the FAL-F model, I think. We create 5 different atmospheres with some combinations, and then we run the code setting a threshold like now with 5 cases, and then we checked that the atmospheres were similar and the code was working. And with this, it's relatively simple, and everyone can do it. But of course, there are these different options where mainly if you have really big cubes where you want to save time, then it's better to classify your profiles on families of profiles, and then invert those profiles with different either initializations but also configuration. So then you can say, okay, if I have Umbra-like profiles or Penumbra-like profiles or Plush-like profiles or Nebula-like profiles or Quiescent-like profiles, then you can start those profiles with different initial atmospheres, but also inversion configuration, and at the end try to build the map. But I guess this is my impression. I only think of that if you have really a huge map, because with the computational time nowadays, I will just try to keep it as simple as possible. One configuration for inversion and for initial atmospheres, and run it for the full map. And then let's see if the results are good, like in this case, that everything is consistent and it's okay. Okay, so then let's go back, because today it's getting a bit longer than usual. So homework, try to run the test I prepared. Just pick small field of view. Don't need to run the 500 times 500 pixels. Play with inversion configuration. I just put one, a reference one, but you can play with that. You have 3 lines in total, so you can play a bit also with the clustering limit. So maybe you said, well, I put a 12.1 or 12.3, and the results were essentially the same, but I gain a factor of 30% in speed. Then okay, go for it. Then extra, try to understand how we created, or I created these atmospheres, and try to develop your own method. I think if you said, well, I really want to have as much as possible, so then create 100 atmospheres. If you said, no, I think 5 probably is enough because I think it's enough, so then just create 5 and try to make those 5 as representative as possible of different scenarios. So try to understand what we did and adapt it for your preferences. I still recommend to use constant certification for magnetic field, vector, and the line of sight velocity. But then try to look for atmospheres that are published or someone has already prepared, where the temperature and electron pressure are compatible, and try to create initial models based on those different temperatures. Next class, I think we may work on the response functions in parallel, but I think maybe what I'm going to do is to take SST data from CRISP for my iron line only, because we are still with SER. And I will explain you how you take filter graph data. In the case of DST IBES should be the same. So how you take filter graph data where you have several spectral points, and sometimes they are not uniformly distributed along the line. How you prepare that for running it with SER, that essentially will be the same for running it with Desire. So I think we are going to do that next week. So small patch and prepare everything for running in parallel and then run the inversion. I hope you are interested on that. Okay. I put it in italics because it's the same message from last week, but I'm going to put a folder inside on the Dropbox folder that I use for sharing the material with you, where I'm going to put the version of the Python wrap and the changes that we made, because we are changing things. And in fact, the one from today, I'm going to change it again because there were some bugs. So then I will try to keep version control. Ricardo will have it on his GitHub, but I will also have it on Dropbox because it's changing. And I know that some of you will probably find some errors, but we will try to keep it updated. And every time we change things, I will try to keep a log. So then you can check if it was something that was you were having problem with, or it was something that you said, okay, that's fine, that is now fixed, but I didn't care too much about that. Okay, and yes, next class next week, Friday. Okay, now it's time for additional questions. Let me stop sharing. Is there any question that you want to ask about the process? Did you follow the process? So we synthesized profile last week. We inverted them today. We devised a way of trying to avoid local minima, but at the same time try to avoid repeating unnecessary iterations on a pixel where we already had a wood fit with 1 atmosphere. So it's a balance in between speed and accuracy. And then with the results, we compared with the original profiles from last week and the original atmosphere from 2 weeks ago. And then you have extra information about the chi-square values that you get, about the index of the atmosphere the code was using. And also there was a file, I didn't read it, where, let me go back just 1 second, very quickly. Sorry, this file inside, sorry, this file, this one results for macro. It's a file that it contains on X and Y and 3 values. And the 3 values are microturbulence, filling factor, and stray light. But as we didn't invert any of them, I didn't read it. But if you are inverting microturbulence, the one, or filling factor, the one file you should read for checking the values the code obtained is this one, okay? Okay. Sorry, that was a bit fast. Okay, again, is there any question? How was today? I think there was a lot of information, but we may revise it again next week when we embed data. So if you feel that it was a bit fast, just try to check it over the week, and then next week, if there's something that was not clear, just let me know. Okay. So no questions? Okay, so then thanks again, everyone, and see you next week. Okay, bye.
Thank you.
Bye-bye.
Bye. Okay, I will stop recording.